the presses! Stop the presses! I got a new root solving technique!
But how fast is it?
What? I don't know. Howdy, welcome to the Arrow 220 video lecture series. In tonight's episode, we are going to be talking about order of convergence. We're going to be looking at how fast root solving techniques converge and find that root that you are looking for. And this is especially useful if you are ever clever enough to come up with your own root solving technique and you want to sell it to the world. You want to tell everybody how fast your technique is and how much better it is than everybody else's. So, as per usual, let's take a look at the slides and see what we're dealing with. So, inside the slides, these are the 220.04 nonlinear equation slides. We have on slide 11 out of 19, we start talking about order of convergence. Talking about the order of convergence is also analogous to talking about the rate of convergence. Higher order means faster convergence, faster rate. There are two main things you got to know. First, the first one is alpha. That's a terrible alpha. Alpha. And that is the order of convergence. And you've got lambda, which is the asymptotic error constant. And generally, lambda is going to be less than, it's going to be greater than 0 and less than 1, general. It's going to be less than 1, general. Ignore this 0.1 thing. It's going to be less than 1. That's what's important. We say that if alpha is 1 for a sequence, that's a linearly converging sequence, which is kind of slow. It's not that fast. Alpha equal to 2, that's quadratically convergent. That's something like Newton's method, which is a pretty fast method. There might be faster techniques out there, cubic or something like that, but I don't know of them. Let me know if you know of one. The thing that we first want to take a look at is the error. So all of these derivations about order of convergence assume that you already have like a true value. So true value already know. And what we want to see is how fast your root solving technique approaches that true value. And so for our purposes, what we're going to call the true value is whatever value your root solving technique converges onto. We don't actually talk about if that's the correct root or the correct value. We're just assuming it is. And if your root solving technique is converging towards it, then we're going to assume that it's converging towards the truth. We're going to call that truth. And we're going to define the error, and by error I mean distance from that true value at each step of the iteration. We're going to define that as E sub n. Now it's kind of unfortunate, the notation in these slides uses this like nice little cursive E, which makes it look like you're talking about Euler's number. It's not Euler's number, it's just error. And that's defined as the absolute value x sub n minus x. So x sub n is your estimate after n iterations. So you've got your, whatever root solving technique, blah. So you're going to start at some initial x sub naught, and then, in theory, whatever the technique does, it's going to get an updated value, and then another one, and then another one, and then eventually, hopefully, find that root. So after n iterations, you have x sub n. X here, that's the true value. That's true. And so we want to know the distance between your estimate and the truth, and that we're calling E sub n after n steps. Now, the critical formula that you have to know for this entire section is right here. I'll write it out here in red. That's the error at the nth step over the error of the previous step raised to the alpha power equals lambda. So basically, we're looking at the ratio between the errors. As you probably figured out, the smaller this ratio is, meaning the smaller the error gets every single step compared to the previous step, the faster you're going to converge to your solution. Oh, excuse me. Oops. Moving on to the next slide. So, here on this slide we have an example of linear convergence as we have the limit as n goes to infinity. I guess this is more of a proof. X sub n minus x, which is e sub n, over x sub n minus 1 minus x, which is the error at the previous step. That equals the limit as n goes to infinity of e sub n over e sub n minus 1. By the way, sorry, this is for linear convergence. We have linear convergence, which means that alpha is equal to 1. This equals lambda. So all that this is saying is that as you go farther and farther and you do more and more steps, eventually the ratio between those errors is going to approach lambda. Now this is useful if you can go ahead and follow these steps over here. That would help you with one of the homework problems. But you can see that for a linear convergence rate, we can solve for the error after n iterations as a function of the initial error times lambda raised to the nth power. So after n steps, we're going to start with this much error, we're going to end up with this much error. This assumes that you already know lambda, and it assumes that you already know alpha, and that alpha is 1. There is a similar derivation for quadratic convergence, where you can see how the error decreases quadratically. Basically, it's a faster converging process. And for that, the convergence formula is for quadratic. After n iterations, e sub n equals e naught 2 to the nth lambda 2 to the nth minus 1. It gets kind of ugly. And if you did cubic, the pattern isn't actually very obvious. It's not exactly clear what that would look like. That's one of your homework problems, actually. Bonus problem. Again, though, this assumes that you know alpha is equal to 2, and that, sorry, this was alpha equal to 1, and that you know lambda. What if you have some root solving technique, you've measured, you've taken it, you've ran it for a long time, and it's converged on some number. Let's call that number the truth. Now you can talk about the error at each step of the process. How can I take a bunch of error measurements and then from that calculate lambda and calculate alpha? Calculate the asymptotic, what was it? Asymptotic error constant and alpha, the order. We can calculate those things. So let's go ahead and see how that is done, because that's one of the key useful things about this chapter. Though before I get into that, let's take a look at, let me just pull up an example here of two convergence methods. So here's linear convergence, and here we have that the error of the nth step compared to the relative to the error of the first step is lambda n. The main takeaway is that here for a lambda of 0.5, you see that the error at each step is halved. So here we have 0.5, here we have 0.25, here we have 0.125. At every step, so it's funny, linear convergence is actually geometric. It's halving every time, so it's like powers of 2, and that's linear. Quadratic convergence is way faster. Like, we cut down by a fourth, and then this fourth gets cut down into 16ths. So this grows, like, this reaches the root ridiculously fast compared to this. The bottom here, it says that it would take, what this achieves in 6 iterations, it would take 126 iterations of this to reach that same accuracy. So quadratic convergence is way faster. But anyway, back to solving for lambda and alpha. So starting from this equation again, like I told you, the key equation. Oops, I totally just botched that. And we know that that equals lambda. That's what we wrote. What we wrote above here. Well, this, for a really, really big n, this is actually, we're going to assume that this is true for the next step as well. That ratio isn't really changing. Lambda's not gonna change. Well, this is convenient now because while previously, if you only looked at this, you had one equation with two unknowns, lambda and alpha. However, now we can write one equation with one unknown. We can write error at the nth step over error at the nth minus one step equals error at the nth plus one step over error at the n at e sub n alpha. And again, these are errors. These are not Euler's number. And so you can follow the derivations here of what's done with this. You basically collect the alpha terms on one side and you take the natural log of this equation. This is why it's important to not treat this like Euler's number, because if you take the natural log of Euler's number raised to some power, you just get that power. It's not what this means. Anyway, might as well do it. Okay, so we have e sub n over n plus 1, e n. Okay, no, they did it different. Not that it matters. Just want to be consistent though. E n plus 1 over n, e to the n, e sub n minus 1, whole thing raised to the alpha. You're going to take the logarithm of this on both sides of the equation. So ln, well, that looks terrible. ln of both sides of the equation, so this whole thing. And you're going to rearrange the terms eventually, but okay, let's write them. Minus ln. And you might need to review the properties of logarithms if you're not sure about how these came about, but trust me, these are correct. Minus 1. And now we can solve for alpha. Alpha is equal to natural log of e n plus 1 minus e n, natural log of the nth error minus natural log of the nth minus 1 error. Super important equation. The question now is, how are we going to get these error values? Like I said, you're going to run your iteration to a point where you consider that you've reached the convergent value. And then from that, you're going to subtract any kind of previous value. So let's say we're going to run our iteration until n plus 2. All right? So that's our true value at n plus 2. N plus 1 is going to be the error of the previous step. N is going to be e sub n is going to be the error 2 steps prior. And e sub n minus 1 is going to be the error 3 steps prior. So that means that if you have to do at least a couple of iterations, you have to have at least like 4 iterations so that you can talk about the 3 previous errors before that last iteration. So from this, we're going to get alpha, and then all we need to do is go back to the original equation. So let's say we know alpha at this point, and then we go back to e sub n over e sub alpha n minus 1, and we just solve for lambda. You just plug that in, plug in whatever error values you got at the nth and nth minus 1 iteration, and that's how you're going to solve for lambda. So this is empirically solving for lambda and alpha. You're not using any kind of analytic formula. So let's look at an example. We have some function here for which we want to find the root, f of x. And we're applying Newton's method to this guy. So we got quadratic convergence rate. So it's going to be a fast convergence rate. Our initial guess is 1.5. All right, initially I want you to forget about these columns. Just ignore them for the moment. Run your iteration for however much you want. In this case, we run it 4 steps. After 4 steps, we stop and we say, this is x. This is true. Let's just roll with it. Let's just assume that that's the true value. Now, with that in mind, we go back, and now we calculate the second column. Once we have this true value, which is this guy. So we're going to go ahead, we're going to calculate all these e sub n's. From that, you're going to take the logarithm of all of these values. Your error here is going to be 0 because we have true minus true. So that's going to cancel out. The logarithm of 0 is negative infinity, so we're not going to use that value. And now basically we just have to calculate alpha based off of the numbers that we've tabulated. And we have a couple of options. So our general formula was alpha equals ln of, I can do it here. So n plus 1 minus ln 1 minus 1. So we have a couple different options for n. N could be 2, and so n plus 1 would be this value. E sub n plus 1 would be this value, or this value. E sub n would be this. This would be e sub n minus 1. Or we could pick n equals 1. You could pick, if n equals 1, then this would be the n minus 1th term. This would be the nth plus 1 term. However, you want the biggest n possible because that's going to give you the closest accuracy. You want to know what this thing does asymptotically, what the asymptotic behavior is as n goes towards infinity. So the bigger the n you can use, the better. So we pick, it looks like, funny enough, they actually, in this example, they pick n equals 1, which is not the most accurate option. That's what it looks like anyway, because this is supposed to be e sub n plus 1. So that's this guy. And then this is supposed to be the logarithm of e sub n, which is this guy. Yeah, so they actually, they could have used n equals 2 and that would have been more accurate. But anyway, you get 1.96. If you use a more accurate one, you'll get some number closer to 2. Again, Newton's method has quadratic convergence, which means alpha should equal to 2. Empirically, as n goes to infinity, this should approach 2. It can be a little bit more or a little bit less. And from this, you go back and you plug in values for lambda, and you see that lambda is roughly 0.4. And this is other stuff. All right, that's all there is to say about convergence rates. And with this, we are actually done with our chapter on solving nonlinear equations. We're going to use this stuff elsewhere later, but this wraps up module number, 5? So congratulations, and thanks for watching.